Okay, today we're going to be talking about the big three theorems. So the squeeze theorem in calculus has to deal with limits, and the fundamental theorem of calculus we won't get to until second semester. And so these are the big three that we know as of right now that are involved in a multitude of ways. And because they involve functions and graphs and tables, very often students can get them mixed up. So this is a wonderful opportunity for you to sort of compare, contrast, differentiate, and come up with your own ways of remembering when to use which theorem in which scenario. Okay, so we in our first unit learned about the IVT, the intermediate value theorem, and this theorem says that if a function or if f is a continuous function on the closed interval a to b. The closed interval just means that you include the a and b on the interval. Another way of writing that would be if you wrote a is less than or equal to b. This is just a different notation for it. And if we know that f of a is less than some value that's less than f of b, so we'll call this value d, for example, then by the intermediate value theorem, there has to be some c on this interval such that f of c would equal that value. And so let's look at visually what that means. So visually, if you have a graph going from a to b, and then we have a function. It doesn't actually matter what the function looks like. It could be curvy, it could be straight, as long as it's continuous. And here is f of a, here is f of b. So these are the x-coordinates of our interval and then their y-coordinates. And let's say that we're looking at this value or the value d that is right here. So d is falling between f of a and f of b. We know since this function is continuous on the interval and then this one of your y values is less than your d and then one of your y values is greater than, there has to be some point between a and b that when you plug that value into your function, you get out this y-coordinate. So basically it's saying that if you have a graph from A to B that is continuous and then some value falls between their y-coordinates, the x-coordinate that attaches itself to that goes in between A and B. Okay, so that's your intermediate value theorem. It basically says that if you have a value that is intermediate between two other functions, or between two other y-coordinates, its x-coordinate must exist as well between A and B. Now, this is different from our mean value theorem, where our mean value theorem says, first of all, it has a little bit more that has to be met in order for us to use the mean value theorem. It does have to be continuous on the closed interval for that same way. And remember, closed interval means that it includes the endpoints. But it has to be differentiable as well on the same open interval. So it has to be differentiable from A to B, but it doesn't necessarily have to be differentiable at A or at B. And then so the mean value theorem tells us is the word mean means average. So it means the average rate of change from A to B is D. So if we find the average rate of change between 2 points and we get out some value, then by the mean value theorem, there must exist some C in this interval such that the instantaneous rate of change will also equal that value. So graphically, let's talk about what this looks like. So I have A, I have B, and then I have, oops, a little higher. So let's say I have some function that does this. Here is f of a, here is f of b. And if I tried to calculate the average rate of change for that, so average rate of change, another way of talking about that is if you did the average rate of change would be the slope, or if you want to do it in actual mathematical notation, f of b minus f of a over b minus a. That's how you evaluate slope, right? y2 minus y1 over x2 minus x1. That's your slope of your secant line. So it basically says, the mean value theorem says that if you have a continuous differentiable function, so a function that's continuous and doesn't have any sharp cusps or corners, then, and its average rate of change, the slope of your secant line is some value, there has to be at least one other point between A and B where your instantaneous rate of change, aka the slope of your tangent line, equals that as well. So basically where your tangent line would have the same slope and be parallel to that. So our graph example actually has two of those, two places where that happens, but the mean value theorem just confirms that there has to be at least one place where that happens. So we can call that one C1 and then C2, but there has to be some place where if you found that your slope, for example, was your average rate of change was 1/2, then there has to be a place where your tangent line, aka your slope of your tangent line, your derivative, also equals 1/2. So that's the mean value theorem. And then last but not least, probably the one that's easiest to understand or like most intuitive is the extreme value theorem, EVT. So as long as you have a continuous function over the interval, the open interval a to b, then by the extreme value theorem, there must be at least one maximum value and one minimum value, minimum, on that interval. And we talked about the like 3 different scenarios that this can happen in. So one of the scenarios is where your relative extrema or your local max and mins are your actual like highest and lowest points of the graph. Like they're the highest and lowest. So this would be an example of that. So your absolute minimum is also a local minimum. Your absolute maximum is also the local maximum. A second example would be if you have a graph where it doesn't necessarily even have to have any local maxes and mins, or that they're not the highest and lowest. So this would be an example of that. So I have a graph that maybe has like, so it definitely has a local minimum and a maximum, but those are not the highest and lowest points on the entire graph. In this scenario, your endpoints would be considered the very highest and lowest. And then you could have any combination of those two as well. So if I had a graph that went from A to B, and let's just say the very highest was an endpoint, but the very lowest was a relative minimum. So this one of your absolutes is an endpoint, where the other absolute is a local relative or minimum, minimum or maximum. Okay, so those are in essence your 3 theorems, and what we're going to do next is we're going to talk about what they have in common and what they or how they're different. So how they're the same and how they're different, and how you can connect them or differentiate between them. So the first thing that we want to notice is that all 3 of these theorems require that your function is continuous on the interval. So continuity is key for using these theorems. Okay, and then they all at some point deal with a regular function or an original function. So they have to deal with f, okay? Now there's some places where that differentiates. So for example, IVT and EVT only necessarily, like they don't necessarily need to have a derivative involved. So could use only your original. Okay, so they don't necessarily need a derivative involved. And the whereas MVT, the thing that makes it unique is that it 100% you're not going to use the mean value theorem unless there is a derivative involved. So that's something that differentiates it. Your IVT and MVT are special in that usually you have to calculate your D value first. So you need to do some calculations first. For IVT, what that usually looks like is for IVT, you usually have to calculate, just trying to pick a nice color that goes along with all of this. you need to calculate f of A and f of B first usually. For a mean value theorem, you usually have to, I'm running out of space, calculate your average rate of change. So f of B minus f of A over B minus A. Okay, whereas for EVT, you don't necessarily have to calculate something. It's usually you're just identifying maxima and minima using the strategies you already know, so you don't necessarily need to calculate a specific thing. And then the other thing that connects your mean value theorem and your extreme value theorem is that those could both involve a derivative. They don't necessarily need one, so like EVT doesn't need one, but these could involve or could use f prime. Whereas your intermediate value theorem, you're going to only use whatever function they give you. You're not going to take any derivatives. You're not going to find any derivatives. You're only going to be working with a function. Whereas MVT involves an instantaneous rate of change, and then EVT, just because maxima and minima are so reliant on derivatives usually, you could end up using f prime. So those are some ways that we can compare and contrast your intermediate value theorem, mean value theorem, and extreme value theorem. And what we're going to do next is kind of work our way through some situations or scenarios and decide which of these theorems are applicable and then actually practice using them.